Hi, welcome back to AB 474, Indoor Environmental Control. We are in our series on psychrometrics, looking at the study of moist air. The first installment was a review of the ideal gas law, and the second installment was building a nice foundation, talking about a little bit of application of the ideal gas law, and specifically talking about pressure. And we are ready now to really dive into the properties of moist air. And so this section we're going to define a variety of properties, of ways to look at and describe our air. And then we're going to take a look at the psychrometric chart. So let's get started. So some terminology that we need to be familiar with begins with the term dry air. So when we talk about dry air, as you might expect, it is the state of air when all moisture and contaminants are removed. For a lot of our psychrometric properties, things are done on a dry air basis. So it's important to understand what we mean when we say like massive dry air. Counter to that, moist air is what we're almost always working with in reality, and it's a mixture of dry air and water vapor. And just to refresh ourselves a little bit about psychrometrics, so it's the study of moist air. But what do we want to do with psychrometrics? So there's two main things we're going to talk about with respect to psychrometrics. We're going to talk about determination of the properties of our moist air. And that leads us to what we really want to get to, which is being able to manipulate those properties. So determining properties at an unknown state after a defined change from a known state. And that's done via what we call psychrometric processes. And as engineers, we like to control and manipulate, so what we really like to do is take advantage of those psychrometric properties to take our moist air from some known state to a more desired state. And so we need to understand the processes in order to know how to get from point A to point B. Let's refresh ourselves again on standard conditions. So we looked at those in the prior segment, but let's refresh ourselves again on what we mean when we say standard conditions. So our standard conditions are at sea level, and our standard temperature that we will work with. So this one is an important thing to note. So various sources are going to use their standard at various places. So for our textbook and for most of the ASHRAE standards, we are at sea level. That's not always the case. So pay attention to your reference if you are using something other than ASHRAE or your textbook as your reference material. So our standard temperature is going to be 15 degrees Celsius or 59 Fahrenheit, and our standard pressure 101.325 kilopascals, 14.696 psi. And again, our reference for this, 2001, 2005 ASHRAE. Right, if we're not at sea level, then we need to make an adjustment for where we are. So how do you do this? So in theory, we talked about it already. In the last section, we looked at the equation for adjusting your pressure based on where you are. But how do you get started with that? So let's look at a little bit of a reference material. So Appendix B in your textbook comes from the Handbook of Fundamentals. So it's taken from there, but you have access to it in your textbook. And it's a table of weather data, so let's grab it real quick and take a look. So Appendix B, weather data, and it essentially gives you a lot of information that we're not going to need for this discussion. We will need it in the future, but essentially a list of weather stations, latitude, longitude, but the column that we're interested in is elevation. So we're going to choose Indianapolis, Indiana to represent us, and we see that the elevation there is 807 feet. And so that's what we're going to use to represent us. We're in Champaign, Illinois. So look in Appendix B in the text. Choose a city that is most representative of where you are and get the elevation. And from there you just apply the equations that we introduced in the last section. So as I said, in our case, we're going to look at Indianapolis to represent Champaign, Illinois at 807 feet. Now, why did we use Indianapolis to represent Champaign, Illinois, and not Chicago? Well, because Chicago is quite a bit north of us, and Indianapolis is closer in terms of our north-south direction. So Indianapolis is actually a better representation of Champaign. And then from that, you'll use the method that we discussed before to calculate your temperature and pressure, or you can use an online calculator or other resource. So then you need to calculate or find the temperature and pressure for the different elevation for where you actually are. Okay, now that we have kind of introduced the next few topics and kind of refreshed our memory on some of what we saw in the last sections, we are ready to really get into the meat of psychrometrics. So, properties of moist air. And when we say the term moist air, we're talking about a mixture of air and water vapor. So it's important to pay attention when you're working in psychrometrics, whether you're talking about moist air, which is the mixture of air and water vapor, whether you're talking about just the air, so we call that dry air, or just the water vapor. So there'll be different scenarios where you'll talk about each one of those, so it's important to pay attention to that. So the first property we're going to look at is humidity, and humidity is a way to describe moisture in the air. And we're actually going to talk about 5 different measures of humidity. The first one we're going to talk about is absolute humidity. Which is the mass of water contained in moist air. So remember, that's the air and water vapor mixture. And it's represented by a mass divided by a volume. The second one we're going to look at in our book is represented by a capital W and is called the humidity ratio. The absolute humidity is not represented by a variable in our book, so it doesn't have a variable in our notes. The humidity ratio is, as it says in its name, it's a ratio. It's a mass ratio of water vapor per unit of dry air. And it is represented by a mass over a mass. So a mass of vapor divided by a mass of dry air. The next one we're going to look at also isn't represented by a variable in your book. It is called specific humidity. And I've seen multiple definitions for specific humidity, so we are going to use the definition that is used by ASHRAE. So in some cases, specific humidity is defined exactly the same as humidity ratio. For us, the specific humidity is going to be defined as, again, a ratio, a mass ratio of water vapor per unit of moist air. And it's represented, again, similarly to humidity ratio as a mass divided by a mass. But the difference in the definitions by ASHRAE is humidity ratio is per unit of dry air, specific humidity is per unit of moist air. Okay, the next measure of humidity we're going to work with is probably the one that you're all the most familiar with. It is relative humidity. And relative humidity is the degree to which the air is saturated. It's often referred to as how the air feels. And it's represented as a percent. So essentially, how much moisture is in the air compared to how much moisture could be in the air. And then the last one we're going to talk about is degree of saturation, which is similar to relative humidity, but has a different type of unit on it. So it is a ratio. It's a ratio of humidity ratios. So it's the ratio of the actual humidity ratio to the ratio to the humidity ratio at saturation. So it's ratio of actual humidity ratio to saturated humidity ratio. And this variable is unitless. Okay, the next property that we're going to talk about is how we measure energy in moist air. And we use enthalpy. So as a measure of internal energy. We represent enthalpy in this book with a little I, which throws me off every time because I'm used to saying a small h, but in our book they use small I, so we have to adapt so that we can follow along. So enthalpy, a measure of internal energy. A way to represent the amount of energy that's stored in our moist air. You might also see this called specific enthalpy. Okay. The next parameter that we are going to use to describe our moist air, actually we have 3 different temperatures that we will use. So the first one is dry bulb temperature, and it might be represented by a small t or a large t depending on whether it's temperature or absolute temperature. And this is dry bulb temperature. Dry bulb temperature is the air temperature that doesn't include any measure of moisture or any relationship to moisture. So I'm going to say it's exclusive of moisture. So there's no consideration of moisture when we take this measure. And it is the true measure of thermodynamic temperature. And it's what we would get if we just measured the air with a thermometer, as long as we shield it from sources of radiation. As long as we expose it to air, there we go, and shield it from radiation. The next measure of temperature that we are going to look at is called the wet bulb temperature. The wet bulb temperature is the temperature of the air if it were cooled to saturation by evaporation of water into the air. So the air temperature, if the air is cooled all the way to the saturation line, and you'll know what the saturation line is in a few minutes, all the way to saturation by evaporation. Excuse me. Okay, and the last measure of temperature that we're going to look at is called the dew point temperature. And the dew point temperature occurs at the point which moisture condenses out of the air. It's also called the saturation temperature. It's the point at which the air can hold no more moisture. And then we have sort of a magical thing called the triple point with respect to our temperatures. So the triple point occurs at saturation. And that happens when our dry bulb temperature and our wet bulb temperature and our dew point temperature are all the same. So that's a really magical place called the triple point. And we have just a couple more properties that we need to define. So rho is our density. We've seen density before. This is just with respect to moist air. So it's the mass of air per unit volume of air. Mass of moisture. I can't use my ability to write here. Mass of moisture per unit of volume of air. And then our specific volume is our volume of air per unit mass. 1 over our density, essentially. Alright, so that wraps up our list of properties that we're going to work with when we talk about moist air. So the next question that we have, how do we get these properties? Well, if we know 2 properties, we can get all of the others. So in the next section, we're going to talk about a variety of ways that we can get all the other properties when we know 2. Before we conclude this section, I want to introduce the psychrometric chart. The psychrometric chart is a graphical representation of our moist air properties. And it's comprised of 7 of the properties. You can get 7 properties directly from the chart. You have to know 2, and then you can get the other 5. Excuse me. It's important to note that each chart is specific to an elevation, and you cannot translate from one elevation to another using the chart, using only the chart. So specific to an elevation or specific to an atmospheric pressure. So before we wrap up this section, I want to just take a look kind of at a skeleton chart. The psychrometric chart can be a little bit intimidating to look at first, so we're going to start with more of a skeleton to kind of orient ourselves to it, and then whenever we get into the next section, we'll look more in depth at the chart and pull some points off of a chart, and we'll also get into discussing other ways that we could get our psychrometric properties. So this is kind of the layout of the psychrometric chart. There are 7 properties represented. Let's start with along the x-axis, and this is our dry bulb temperature. So each of these lines is representing dry bulb temperature. And then our dew point temperature is represented by the horizontal line, so dew point, and that's typically read along this line, so there's a scale along this line. Our wet bulb temperature is this diagonal line, and you'll see a series of diagonal lines. The curved lines are relative humidity, and they go from 0 to 100%. Not all charts have all the way to 0 and all the way to 100%. Along the y-axis, this is our humidity ratio. This line here is called the saturation line, so this is 100% relative humidity. We have another set of diagonal lines that are a bit steeper. These are called specific volume, or 1 over density. And then the last property that we can get off of here is our enthalpy, and it runs lines that are very, very similar in slope, but not exactly the same as our wet bulb temperature. So this is a brief introduction to the psychrometric chart, and in the next section we'll look quite a bit closer at it, as well as other ways to get our psychrometric properties.